Well, good morning, good afternoon, and good evening, wherever you are in the world, and welcome to Photonics for Quantum 2 once again. I'm Don Feiger, your host, broadcasting live from an undisclosed bunker in Rochester, New York, near the Rochester Institute of Technology, but not quite at RIT yet. We're still in quarantine here, and we've had an exciting week, a very full week, and we started out Monday with a government panel discussion from representatives of NASA, NIST, and NSF. They told us about their quantum projects and their future plans for quantum. We also had a bit of excitement the very next day when NSF announced three of their National Quantum Leap Institutes, and they chose three in this round, round one, and then they're going to run round two starting in September when the preliminary proposals are due. And in round two, they'll probably pick another two or three. So the winners this year are University of Illinois in a consortium with University of Chicago and University of Wisconsin, and then University of Colorado Boulder, and then finally University of California, Berkeley. So congratulations to all of them. Let's see, the following day we heard from Saikat Guha from University of Arizona, and then Wednesday, David Starling from Penn State Hazleton. And then yesterday, we had an exciting event first for us called Women in Quantum, where we had quantum experts in the field talk about their experiences being women and doing quantum. And most of them were at companies or agencies, and some were former professors. So that was exciting, and it got a lot of participation, about double the amount of participation that we've had for the talks. So I encourage you to go back over this past week's talks and panels and take a look at the videos if you haven't seen them. You can do that by going to the RIT PFQ2 webpage, looking at the program, and you can click on any of those talks, at which point you'll get an accordion that expands downward. And at the top of the accordion, you can see a link for the video and for the slides. So rounding out this week, we have a talk from Li Qian of University of Toronto, followed by a poster which is going to be given by Junyali Narayal on behalf of Jaime Cardenas' group at University of Rochester. And a little bit of a program note here. Next week, we start off with a talk by Andrew White at University of Queensland. The problem is we don't have the title yet, and we don't have the time yet. Now, he's on the other side of the world, so I don't think he's going to be talking at 1 p.m. We just haven't heard yet what time we're going to settle on. It could be 9 a.m. or it could be later in the afternoon, like 5 p.m. in order to suit his time there. So hopefully we'll get an update soon and post that to the website. So please check. It'll also be listed on the announcement that you get on Monday morning. Let's see. Otherwise, we have a full week of science talks, and we don't yet have sponsor talks or poster talks. So before passing it on to Lee, I just wanted to say thank you to our generous sponsors whose logos you can see surrounding my image here. And without their generous contributions, we wouldn't be able to deliver this content free of charge to you. So thank you all to our sponsors. So Lee, please take it away.
Thank you very much, Don. Let me first try to share my screen.
I can see your slide.
Okay, great. Thank you. So first of all, I'd like to thank the organizer of the workshop, is particularly Don, who gave me this opportunity to speak here. It's a wonderful workshop, and I'm very glad to be part of it. So today I'm going to talk to you about fiber optic quantum entanglement sources. I come from the background of fiber optic telecommunication. I worked in Corning for 3 years before I joined the faculty of at the University of Toronto, and that's before I started my sort of quantum career. And I still have this special attachment to fiber optic, and I was very lucky to give the opportunity to merge the two fields. Now I think fiber optic has, even though it's a mature technology, it has great potential in being applied to quantum technology, because fiber has the lowest loss, carries the largest bandwidth. And fiber, even though it's when you think of silica, you don't think of its nonlinearity, but one could argue silica is both the worst and the best material for nonlinear interactions, even though it has very low nonlinear coefficients, but it has very, very low loss. So nonlinear interactions requires propagation length, interaction length. So fiber, in fact, can play a big role in this. So I hope my talk will convince you that. First of all, I'd like to thank the people who made this happen, my grad students. This is my group, remind you of very cold Canadian winter. My group currently is where a lot of them are working in quantum key distribution systems, but some of them are working in entanglement sources. So that's including Arash, Chanzia, and postdoc Dr. Eric Zhu, who's also a former PhD student. I also like to thank my colleague, Professor John Sipe from Toronto, provided theoretical guidance. Professor Peter Kazansky from Southampton and Dr. Alexei Gladyshev from Russia. They both provided expertise in fabrication of the specialty fiber that we need. I also like to say that we have a postdoctoral position open, so if you're interested in the topic, please contact me by email. Okay, so first to give some background motivation of the work we do. So, you know, I don't have to convince the people here that quantum technology is both interesting and can have great potential. I'm preaching to the choir here. But let's step back and look at optical technology. Starting from the first invention of the first laser, Neimann's ruby laser. At that time, it's just a lab curiosity, right? But a number of decades later, it led to 650 billion industry globally, possibly even more. This number is a bit outdated. I think the fact that the photonics technology took off largely due to the development of laser sources. And starting from the invention of the first laser and several decades later, the development of the laser sources basically becomes, the laser sources that's been developed became more practical, meaning they're more reliable, longer life, lower cost, compact, easy to operate, and all of that. That's what I mean by more practical. There are also more variety of lasers being invented. There's different wavelengths covering from UV to far infrared. There's short pulses, long pulses, CW laser, narrowband, broadband, tunable laser, so on. And I think all of that enables the flourishing of the optical technology. Now, in parallel, we're seeing the starting of quantum technology. And after all, I'm from the engineering department here. I'm not a physicist. So if I'm doing quantum technology, that means, you know, we are in the track of making it a practical technology. And starting from Paul Kwiat's first entangled photon sources back in 1994, 95, I think there is a need to develop more practical and more variety of quantum sources and entangled photon sources. So that's basically the motivation. And what I'm trying to convince you today is that fiber optic technology is actually very well suited to make these practical and these flexible, versatile quantum sources. So basically, they're just two messages. One is a practical quantum source, and the other one is a versatile source. So what do we mean by practical? For me, to claim something practical, it has to be practical enough for a company to want to build it, and for a company to think that they can sell it and make a profit. Yeah, so this is Odds Optics entangled photon source. Is one of their new products, and it's entirely based on the technology, the fiber-based optical, fiber-based entangled photon source technology that we developed in our lab. And now I'm very happy to see that by working with Odds Optics, commercialization effort has brought it into the real world. So what is the core technology that we use for entangled photon generation? The key technology or the key component of this device is what we call the periodic poled silica fiber. So the photon pairs are generated through what's known as spontaneous parametric down conversion, or SPDC process. It's a common process that's used to generate entangled photon pairs in a large number of nonlinear medium. But what we use, what's special about this is this is in optical fiber. And in fact, I think we're the only group that uses SPDC, a second order nonlinear process, to generate entangled photon pairs in optical fiber. Obviously, why optical fiber? Obviously, there's a number of justifications. It's silica fiber, so it's compatible with the telecom network. We can splice. The fiber doesn't need any alignment. You can splice it to the telecom fiber. It's a step index silica fiber. The mode is well matched to the telecom fiber, meaning that ultimately you can get very low loss, right? So from the generation to ultimately sending out to the quantum internet, if you like, there's very low loss. And loss is, I guess, the single most important issue in quantum technology, I believe. So fiber has its great advantage. I'm going to tell you some other advantages with fiber. Now, in our technology, it's completely operated in room temperature. There's no need to cool the fiber. It's alignment free, as I mentioned. All you need is to splice, splice at the input end, splice to a laser diode, at the output end, splice to some filters, and go to the output port. So there's no moving part, there's no alignment, no adjustment of fiber coupling, and so on. And it's completely compensation free in the sense that we don't need an additional step to compensate for the temporal or spectral distinguishability of these photons to get a high quality polarization entanglement. So I'm going to talk more about it later. All right, so let's first talk about this periodically poled silica fiber, what it is. As you know, that fiber, well, silica glass, it's an amorphous matrix, so it doesn't have any symmetry. So normally it doesn't have any second order nonlinearity. So you cannot do SPDC in fiber. So if the first step is we have to induce nonlinearity. Now this technique is in fact known for a long time, how to induce second order nonlinearity in optical fiber. What we use is a twin hole fiber, as you can see here. This is the cross section. There are two large air holes, and the middle white part is the core of the fiber. That's where light travels. So to induce nonlinearity, we need to break the symmetry, right? And we use an electric field to break symmetry. So the electric field, first of all, we insert electrodes into these air holes. That's why it has two large holes. That's for insertion of electrodes. And then you can apply a high voltage on the order of 8, 9 kilovolts or so. At the same time, you heat up the fiber to 200, 300 degrees C. At that temperature, the impurity ions in the glass matrix becomes relatively mobile. So they're going to drift under the influence of the external electric field. Okay, and after some time, typically about half an hour or so, you can cool down the fiber back to the room temperature, and you can remove the electrodes. So there's no longer any external electric field. But because the fiber is now at room temperature, these impurity ions, they will not move. They're frozen in the glass matrix. And as a result, there is an electric field due to these impurity ions in the glass matrix, and that is around the core region. And that establishes an internal electric field. So this electric field is not supplied by the electrodes externally. It is an internal built, frozen in electric field in the glass. And this is the electric field that breaks the symmetry. And with this DC electric field, there is an induced effective second order nonlinearity, which allow us to do parametric down conversion. Of course, to make this process efficient, we also need to do quasi-phase matching. And that can be done by a process we call periodic UV erasure. So UV light apparently can erase the nonlinearity that was generated through thermal polling. And we erase it point by point in the periodic fashion, and to make sure the period is corresponding to the quasi-phase matching period, so that we can get an efficient nonlinear process, second order nonlinear process going on. And as I said, this technique has been developed for quite some time, since quite some decades ago. And it's being used now for entangled photon generation. Now, notice one thing though, if you look at the cross-section of the optical fiber, that it does have a slight polarization dependence. So the horizontal direction obviously is different from the vertical direction, right? So the optical mode, you expect it to have slight polarization dependence. So there's a very, very weak polarization dependence. And this weak polarization dependence allows for a weak birefringent phase matching, in the sense that if you do second order nonlinear frequency conversion, for example, in this case, second harmonic generation, right? If you do second harmonic generation with this piece of periodic poled fiber, then you will see 3 peaks. And these are the different phase matching types. This is type 1, type 2, type 1, type 0, and type 2. And they correspond to different combinations of the fundamental photon polarization and the second harmonic photon polarization, right? Now, and the fact that they are at different wavelengths is because the birefringence of the fiber allows the birefringence phase matching that separated these processes. The process of interest is this type 2 process. If we think of the reverse process from the second harmonic generation, we can have a vertically pump photon at around 774 nanometers, right? And then go through a spontaneous parametric down conversion that will give us a photon pair, and it is polarization entangled, because there's one would be H, one would be V. Right? It's a polarization entangle. So this is a type 2 process that is separated from the other phase matching processes. And this is the process that allows us to generate polarization entanglement. Okay, so if we look at this type 2 process, we have to pump around this peak. If you look at the pump wavelengths, that's fairly well defined. It's very narrow band acceptance for the pump wavelengths. But if you look at the phase matching condition to allow the signal and idler bandwidths, it's very wide. So what we plot here is the signal idler bandwidths, signal and idler wavelengths versus the pump wavelengths. And if you tune the pump wavelengths in this region, this is only about 1 nanometer or so, this whole region. And if you put the pump, if you set the pump at this specific wavelength, we can have an emission over about 100 nanometer or 80 nanometer at least, broad emission of these biphotons. These photon pairs will have 100 nanometer or so bandwidths. And this is shown here, where we have the you can see the sum frequency of signal in idler is very well defined because that's defined by the narrow pump frequency, but the emission can be very broad, about 100 nanometer or so. Now, that says the two photons are frequency entangled, right? But they're also polarization entangled. And as we know, to get good polarization entanglement, it's not sufficient just to generate these pairs. You have to make sure that they are indistinguishable. And if there are some distinguishability, you have to erase it to recover the high quality polarization entanglement. And in our case, what about the distinguishability? If you look at the quantum wave function, the biphoton wave function that we generate, that you can see that there are two spectral amplitude associated with the F function that is associated with a horizontally polarized signal, vertically polarized idler, or the G function that is associated with a vertically polarized signal and horizontally polarized idler. Now, if the F and G are completely identical, then you have the highest quality of polarization entanglement, because then you can just factor out the frequency dependence and you get HV plus VH, the psi plus state. Now, if you look at, if you write it out, the F and G function, you find that there is a phase factor, and then there is also a spectral envelope. And the difference in the phase factor of the two functions gives us temporal distinguishability, whereas the difference in the sync envelope, that gives us the spectral distinguishability. And you can see that both are dependent on these betas. Betas are the propagation constants of the modes, right? So betas can be slightly, in our case, very slightly polarization dependent, as well as wavelengths dependent. So the question is, now, I said that our source is compensation free. That makes it so much simpler. You don't have to do any additional compensation or erasure of distinguishability or erasure of which way information. But the question is, why is it compensation free? How come it's not for crystals? And what is the condition that you need to meet to make the temporal distinguishability and spectral distinguishability negligible? And it turns out, so this is published in a paper some years ago, it turns out there's only one condition that you need to meet. That is that if your chromatic dispersion over the bandwidth of the signal and idler emission, so the chromatic dispersion over that bandwidth is much larger than the polarization mode dispersion, then you're good. Then you do not need to compensate for spectral and temporal distinguishabilities, and you can get a very simple, truly compensation-free entangled, polarization entangled source. So that's, and that is the characteristic of the optical fiber. And if you, if you look at our fiber versus some other material system, so what's plotted here, the horizontal axis here is basically, you can think of a chromatic dispersion, and it's beta 2, second order chromatic dispersion. And the vertical axis, you can think of it, it's a polarization mode dispersion, right? How much walk off the two polarizations walk off from each other over the distance of this nonlinear medium. You see the polarization mode dispersion is orders of magnitude lower than other material systems. So this is BBO, this is lithium niobate, and this is L-gas waveguide that's used Bragg reflection phase matching, Professor Armor Helmy's group's work. But you see the PPSF stands out because the birefringence is so much lower compared to the chromatic dispersion. And that is why, even without compensation, we can get a very high polarization, very high degree of polarization entanglement, which is measured here using the concurrence. If you look at our density matrix, this is without any background removal or anything. This is just a raw density matrix come out of the measurement. It almost looked perfect. And this is because of this, this compensation-free characteristic of the fiber. The other characteristic of the source is its very broad bandwidth. So as you can see here, also because of a low dispersion, you can get broad bandwidth. So what we have here is at least 80 nanometer of bandwidth. So, so you can see because it's compensation-free, alignment-free, room temperature operation, very simple construction, and that's why it's practical enough to be commercialized. In fact, this is the actual specification you can find in Oz Optics website. So these are typical numbers. These are not, one-off hero experimental result. This is the, guaranteed. This minimum is the guaranteed performance of the device. And even so, you can see very high fidelity, very high two-photon interference visibility. And decent amount of pair generation rate and with very broad spectrum. So I hope it convinced you that we have, using fiber optic technology, we can build a practical quantum entanglement source. Now, the next question, let's look at the versatility of the source. Can we make it somehow tunable, or can we shape its spectral shape? Can we do something about tuning its polarization? So this comes from, as I mentioned before, it draws a parallel with lasers. Right? When you have lasers, you don't have just one type of laser, you have a variety type. You have in time domain, you can have continuous wave, Mode-locked, frequency domain, you can have narrowband, broadband, and in the polarization domain, you can have a linear, circular, or depolarized polarization states. Now, if you think about quantum sources, obviously, to make quantum technology useful for a variety of applications, one would like to have a source that also has, at least have a variety of these sources. So for single photons, well, similar to lasers, you'd like to have, time domain, frequency domain, and polarization domain. You can have various properties. But for biphotons, what is interesting is not only you can shape the individual photons' properties, temporal, spectral, or polarization properties, but there's also the correlation of the two photons that you can also shape. You can shape its correlation time, right? Long or short correlation time. So this is not the temporal shape of one photon. This is the correlation time, biphoton correlation time, or correlation spectrum. Or you can shape the degree of entanglement, how entangled these photons are. So there's a very rich space you can explore even just with two photons, right? The message you want to send is to have these quantum sources to meet a variety of practical applications. We need to have a variety of practical quantum sources.
But Lee, we have a real-time question from Paul Qian. If you'd like to take that now, I can read it to you if you'd like.
Oh, sure, yes.
Sure. So he asks, what sets the phase so that you get psi plus and not some other HV plus E caret 5 EH state?
Again, it's because these two, so this is the phase, because these two are very, very similar, because very low birefringence. I don't know if is that okay? These are the phase, because they propagate in the same, and the birefringence is so low that they have the same phase.
Okay, I guess we can go on from here. Then afterwards, if Paul wants to jump on, he can continue.
Okay. All right. So So let's look at the biphoton spectral shaping. So basically, there are two types of techniques. So you can generate using pretty simple nonlinear medium. You generate these biphotons, and then you can do some external spectral shaping using filtering and so on. So for example, Professor Andrew Weiner's group, they use pulse shapers. You can shape it. Now, the drawbacks of this is it's a little bit wasteful in a sense. When you filter, you throw away photons, and these quantum sources, they don't want to, you don't want to throw away photons, right? You want to, they're much more sensitive to loss compared to the laser sources. The other way is perhaps you can, in the process of generating, you can try to engineer your nonlinear medium and make it, shape the biphoton spectrum. So you can, in this particular case, Alex Serjanko's paper, that they have done this aperiodic quasi-phase match, aperiodic polling of the lithium niobate crystals, and then you can custom make your polling profile, you can custom make your spectrum. But this is, on one hand, it requires more complexity in fabrication. On the other hand, it is not tunable, right? It's fixed once this is made. And also in these techniques, there's only the spectral shaping and not polarization shaping. So we want to do something, more ambitious. We want to do something that we can do both spectral shaping and polarization shaping. So the technique that we followed is basically nonlinear interferometer. So if we have the, in this case, individual, so this is just one PPSF generating this wave function. In this case, I just make them the same, the F and G function. They're very similar in our case. And here, let's just, start with simplification. They're the same. Now, if you have another a nonlinear medium, you also generate. And then if you can generate them coherently, then you can interfere the two biphoton wave functions. And if in the middle you have linear medium, then you can change the dispersion to control the relative phase relationship between the two biphoton functions you generate, and also, if you have a control on the polarization, so you can rotate the polarization of the first wave function versus the second wave function, and you can do this simultaneously. And then if you work out the math, then you can basically have a lot of control on the amplitude in front of each one of these terms. So in a sense that you can generate almost arbitrary polarization state, arbitrary biphoton polarization state, arbitrary state generation. So that gives you a great deal of flexibility. And you can do both spectral shaping and polarization shaping at the same time. So, and it's a very simple type of implementation, and it's very suited to the fiber-based source that we have, because as you know, you can have this nonlinear medium, and in this case, we are using a reflective configuration so that we only need one nonlinear medium, but it is still a nonlinear interferometer because the biphotons generated when the pump is going through this nonlinear section in the forward direction. And there's also biphoton pairs generated when the pump is being reflected and generated in the backward propagation direction. And you have interference of these two biphoton functions. So you have a nonlinear interferometer. And in the middle here, you could add a dispersive fiber. In this case, just a single mode fiber is good enough for us. And you can have the inline polarization controller. that can give you the different polarization rotation. So everything is very, very simple. As you can see, this is experimental graph. You can hardly see the PPSF, but you see the polarization controller, and the reflector is just the some metal coating at the end of the optical connector. And as you know, interferometers are typically, they'll be very sensitive to phase stability, right? When you build interferometers, phase stability is usually a big headache. But in our case, it doesn't really matter. That is because the pump, the signal, the idler, they all go through exactly the same optical path. So the kind of phase fluctuation will affect all of them. And in return, we have complete phase stability. So that's another advantage of using fiber-based common path configuration for nonlinear interferometer. So this is some simulation results. Just use two elements. You can, and by changing the dispersion and by tuning the pump wavelengths a little bit, you can get different shape. This is an experimental measurement. As you can see, they're fairly good correspondence to reproduce the simulation. And if you do multiple segments, not just two nonlinear elements, but multiple, and we're being realistic here, we're not asking you to do 100. This is all done by, less than 5 elements. You can get a number of interesting spectral shapes. And you can even get a cone-like type of spectral shapes, and without using filtering, without wasting any photons. Another part we want to talk, we can also do polarization shaping. So this is where we have, let's say, two nonlinear elements. In between, it's a linear element. Now, in this case, if we do incoherent pumping. So the biphoton generated here is incoherent with the biphoton generated there. That we can do by control the pump coherence length. When we do that, we can generate mixed states. So here we have a pure state here, a psi plus state generated here, and a psi plus generated here. And if we keep the polarization controller to give a, let's say, identical matrix, then we also have a pure state coming out at output. But if we rotate the polarization, then we can end up with a mixed state. So as we see here, this is when in one polarization controller setting, this is the output of the entire structure. We have a high degree of concurrence, highly entangled photons, or we can end up with a very low degree of concurrence. This is a mixed state. So that's when with incoherent cascade. Now, back to the coherent case. Now, if the pump, if these two biphoton wave functions are still coherent with each other, then depending on the polarization rotation and depending on the dispersion, we can also couple these two degrees of freedom. We can couple the spectral degree of freedom with the polarization degree of freedom. In some case, people call it, classical entanglement of degrees of freedom. Let's not, put that aside what we call it, but we find that the spectral degree of freedom and polarization degree of freedom can be coupled in there, and the result is that if you see here, we end up with this shape. Now, this shape looks just the same as before, but here what we're plotting is the concurrence versus wavelength. So it is the degree of polarization entanglement versus wavelength that we can, by simply just adding, controlling the polarization controller and adding a dispersive element here, we can have this relationship, which means now, if we use, if we now post-select the photon pairs that's corresponding to high concurrence, we have really maximally entangled photons, or we can have product states with very low, with zero concurrence. We actually did this experimentally, and these are the experimental data that correspond very well with the simulation. And as you can see, if we take these two pair, like these pair of photons, we get a pretty good entanglement. And if we took these pairs of photons, it has a messed up state, which is it's in fact very low concurrence. In this case, the product state. But if you look at the brightness, so the spectral brightness doesn't change for this particular case. We can maintain the high brightness and then simply select, by tuning the wavelengths, we can tune the concurrence, the degree of polarization. So I hope I've convinced you that this common path nonlinear interferometer, especially in fiber-based systems, is very convenient to implement. It's stable. It offers the ability to tune both the polarization as well as the spectral domain, and you can do it simultaneously. So it gives this very versatile source. So that's our basically current directions, and the future directions. We are looking for applications of these entangled sources, quantum sources, and I'm really open for collaboration for people who think of, what application can you think of to use this kind of a tuning of, you need a tuning of entanglement, and you can do it by spectral tuning. So that's what we have. In terms of the applications we have demonstrated, we've demonstrated entanglement-based QKD, sort of a proof principle network where you can combine our entanglement source with a wavelength selective switch. Then you can have a reconfigurable QKD system where you can connect any user with any other user on the network and do quantum key distribution. So that's what we, sort of a proof of principle demonstration. We can also turn the problem backward. We could say, well, if we know the dispersion, or if we adjust the dispersion, we can get a specific spectrum. But on the other hand, if we measure the spectrum, then we can extract the dispersion information of the linear section. So this is sort of a metrology example where we look at the biphoton interferogram in the frequency domain, and we fit it with a specific phase profile. And that leads to a measurement of dispersion of this piece of fiber. In this case, it's just a single mode fiber. So to summarize, basically, it's our core technology is a periodically poled silica fiber. I hope I've shown you that it's practical enough and it's have resulted in a commercial device. And then we have the we can also make it easily into a nonlinear interferometer, and that gave us a variety of different additional functionalities in terms of biphoton state tuning, and it can be also used in applications in quantum network and even metrology. So I'm going to stop here and be happy to answer some more questions.
Okay, I'm going to clap on behalf of all the muted participants. Thank you, Lee, for an excellent talk. We had the real-time question from Paul, and now we have the have another question. Are you able to read that, or should I read it to you?
I'm not. I'm sorry, I didn't start.
Okay.
Let me look at the chat here. Okay, yeah. Oh, here we go. What sets the phase? Oh, okay. I apologize, Miss. Does the spectral control allow the creation of spectrally unentangled? No, unfortunately, we don't have the spectrally. We don't have the capability of creating spectrally unentangled states. We can create polarization unentangled state, but not spectrally unentangled state. So that's something that's a harder problem for us to crack. So basically, we need to broaden the pump acceptance bandwidths. So we probably have to use a much shorter nonlinear medium. And but that unfortunately will reduce the conversion efficiency.
So there's one from me.
Okay. Explore these techniques and materials that allow visible light. Yeah, I thanks for the question. I get asked this question a lot. Though we haven't explored, in principle, this method should work for a variety of wavelengths because it's really just on the quasi phase matching period, and that could be done fairly easily in changing the period. The only other thing is if you want to go to other wavelengths, say visible, we have to redesign our fiber. And basically, you know, to get this fiber fabricated and drawn and then to spec, it requires a number of iterations, and it's also a fairly high investment. And so that's the reason that we haven't really explored these. Also, our funding is also quite limited, being in Canada and everything. But in principle, it can be done, and we are, you know, really interested in extending the wavelengths. So so far we've made a 1550 source and a 1300 source, because that doesn't require a different fiber being drawn. We're really interested in a lot of people ask us if we could make 800 nanometers. So we're interested in going there with 400 nanometer pump. We think that still shouldn't be a problem. There's also another scenario where we have 532 nanometer pump and having the two signal idler, one in the telecom range and the other one in the 800 range. So those are the common things that we're interested in trying if we could could get a variety of fibers made.
Okay, Lee, it looks like you have another one from Katiana.
Oh yes, hi Katiana. How you deal with extinguishing the pump light. So the pump light, so after the photon pair generated, it does get spliced to a standard a standard filter that basically provides 100 dB of pump suppression.
Okay, one from David Starling.
Oh yes, hi. Can you comment on the ability to tune the atomic resonances and or narrowing the bandwidths to suit? Yes, I understand where you're coming from, but unfortunately, currently we can only generate the broadband. I know there's a lot of interest in aiming for narrow bands to couple with atomic resonances, and we are not well. An easy way would be, you know, filter it, because we generate a broadband, and you can always use a tunable filter to find the resonance. But that also means not using the photons very efficiently. But to make a narrow band, there are some ideas we're exploring. For example, a counter-propagating signal idler and so on. So there may be, but that would deviate considerably from our fabrication process here. That would need a much finer grating. So there's some practical difficulty in achieving that. So right now we're not pursuing the narrow band for the time being. But thanks for the question.
You have another one from Paul Kwiat.
Could you poll with electrodes outside the fiber? Then you won't be. Yeah, unfortunately, there's been a lot of study on the polling process itself and optimization. Excuse me. Unfortunately, the strong electric field and the induced Kai2 effect seem to be only limited to within about 10 to 20 microns from the electrode, from the anode specifically. So because it's standard fiber, because the cladding is fairly large, the core is small, the cladding is 125. So if you put the electrodes outside, then there's about 65 microns of distance, and there's just not enough. One is you would need you also would need a much higher voltage, so there's breakdowns and so on that we have to take care of, but also the induced field would not be close to the core of the fiber. So that's one reason that it's not done with the electrode outside. There are people who've done D-cut fibers so that, you know, at least the one side is close to the core. But again, that also require drawn different fibers for that. Basically, or you have to polish the fibers. So we haven't explored, but you know, with enough resources, we could explore some of these alternatives. Sorry, and one from Qian. Have you applied your source in any kind of sensing metrology application? Not really, other than this this demonstration of dispersion measurement. Which is really like a you know, toy demonstration of what this source can do, and obviously the source with such a broad band can do a lot more than just dispersion measurement. So yeah, that's another area that we're looking at. Another one from David: what sort of brightness would expect such a narrow filter? So currently the brightness is, we have millions of pairs per second, but that's over you know, 100 nanometer of bandwidth. So so if you divide that by 100, so that's per nanometer, you're talking about maybe 10,000. What is it? Yeah. Tens of thousands of yes, tens of thousands, yeah.
Okay, it looks like that's it, right, Lee?
Yes, it looks like that's it.
Okay, fantastic. That was an incredible volley of questions at the end of a talk, maybe the longest set of questions I've seen this whole webinar series.
All right.
Yeah, it was a great talk. And as you all know, the recording is going to be posted on the website later today. Now we have coming up a poster presentation by Juniyali Norial at University of Rochester. So I'm going to stop this recording so we can splice it.